Okay, so this kind of HL level stuff for atomic structure really just expands a little bit on the energy level things that in the emission spectrums that we looked at earlier this week, okay, on Monday. Essentially, we get to what we call the convergence limit. And so from earlier this week, we learned that converge means that they get closer together. And so what we need to know for our atoms, for the energy levels for the electrons, is that the energy levels, they get closer together at higher energy levels. So if we look at hold on, somebody's in the waiting room. So if we look at the energy level diagram like this, okay, we can see that obviously down here at n equals 1, the ground state, and then where n equals 2 is, the distance there is a lot greater. And as you go up, they get closer and closer together. And so what happens is you reach what you call the convergence limit, where really they can't get any closer together. So what it says here is, it says in an atom, the highest possible energy level corresponds to the frequency at which the spectral lines converge. So you're going to go up through energy levels, and then eventually you're going to get to what they call n equals infinity. And what happens when you get that high is that really your electron is not going to be held in your atom. It's going to be able to escape, and that's when it becomes an ion, okay? Because if an electron absorbs if it absorbs enough energy, then it can jump so high that it goes out of the atom. It loses that electron, and that's when it would become a positive ion, okay, a cation. And so what this says right here is, it says by determining the frequency at which these spectral lines converge, which is known as the conversion limit, we can calculate what's called the ionization energy. And the ionization energy is the amount of energy that's required to remove one electron from a gaseous atom. So you'll have your element, and you have it, make sure it's in the gas state. That's included in that definition for ionization energy. And so it's in the gaseous state, and then what happens is, if it absorbs enough energy, then if it reaches what we call the ionization energy level, then that's going to be enough energy that the electron can actually escape from the energy levels. And so that's what's happening here. Is it says if we calculate the frequency at which they converge, and then we can use that frequency to calculate the ionization energy. They're related by an equation, okay? And so kind of down here at the bottom, it's kind of saying a little bit about what I said about if enough energy is supplied, then one electron in the hydrogen atom can be promoted to the infinity level. And when it reaches the infinity level, really what we're saying is that the attraction of the nucleus is so weak, because it's so far away, that electron can be removed from the atom. And so then it turns into a positive hydrogen cation. And so this right here, this little equation, this equation is what you would what you would write to represent ionization energy. You would say, I'm starting with a gaseous atom. Okay, so notice that the H has the little G symbol for gas, because it's in the gas state. So it has to be in the gas state for this to happen. And then what happens is that if it absorbs enough energy, what you end up with on the product side is you still have the hydrogen in the gas form, but now it has a +1 charge because we took away an electron. Here's the electron right here, okay? It could go the other way. We could flip it. If we have a hydrogen atom, it could take on the electron and become the atom again. But for ionization energy, since it has to do with removing an electron, then this is what your equation would look like, okay? And so we can calculate the amount of energy that's required to do that. So that's what this last bullet says. The amount of energy required corresponds to the energy that the electron would emit if it fell all the way back down to the n equals 1 energy level from the n equals infinity. So that difference, that would be the amount of energy that's required to ionize the hydrogen atom and turn it into that positive ion. And so we can calculate that. There's two different equations, which if you haven't watched the videos on Canvas, then I would highly encourage you to watch those, because it goes into more detail about these two equations. But essentially, this second one, this is the one to calculate the energy. Okay, so E is going to be energy, and it's measured in joules, which is a capital J. Joules is Joule. And then the little weird looking V, that is actually your frequency. So frequency is represented by a Greek letter, and the Greek letter is called nu, and it's spelled N-U. And so nu is this kind of fancy looking V symbol, which is what we use for frequency. So in order to calculate energy, you multiply the frequency by this letter H, and the letter H is called Planck's constant, okay? And again, it goes into more detail about this in the videos on Canvas. It goes over each letter in these equations, but Planck's constant is H, and it is always this number right here. It does not ever change. And so it's actually in your data booklet that you have to use on your exams for IB. So you don't need to memorize that number. You don't really even need to memorize these equations because they're both in the data booklet as well. You just need to know how to use them and when to use them. So if you're given the frequency, then you just use this equation. So you just take the frequency, multiply it by the Planck's constant, and that gives you the energy. And so that's kind of what they've done here. The other thing you might see is, for example, on this problem in the notes, they did not give us the frequency. They gave us the wavelength, okay? And so what happens is if they give you the wavelength, you're gonna have to use two formulas, because you're gonna have to use this one first and use the wavelength and the speed of light to calculate frequency. So what you would have to do, I'm gonna clean off some of this here so I can write a little more. Okay, so what you would do if they give you the wavelength, first off, a lot of times they will give you the wavelength in nanometers. So Nm equals nanometers. Because waves are very, electromagnetic radiation waves are very, very small. So nanometers is typically the unit that we use to measure them. But in our equation, we have to convert to meters, okay? So if they give you nanometers, which a lot of times they will, to go from nanometers to meters, I need to multiply, or actually no, not multiply, divide. Let me erase it. So I need to divide by, and it's, you have to divide by 1 times 10 to the negative 9th. So it's in scientific notation because it's very, very small. No, I'm sorry. You divide by 1 times 10 to the 9th. Sorry. So if you notice, that's what they did here. So look, it's 91.2 in the problem, but now here down in our work, it changed to this 9.12 times 10 to the negative 8. That's because what they did is, and I can kind of set it up really quickly, they did 9.2 nanometers, and they just did a quick one-step dimensional analysis conversion. So they said 1 times 10 to the to the 9th nanometers is 1 meter, okay? And so they divided by this 1 times 10 to the negative 9, and that ends up giving you 9.12 times 10 to the negative 8th power. So anytime they give you nanometers, you always need to divide by this first to convert it to meters. Once you have it in meters, then you can plug it into your problem, okay? If the way that this equation is set up right here, okay, C is what we call the speed of light. And the speed of light is constant. It does not change, okay? As long as you're going through air. If you're going through like water or a different substance, it's going to change. But most of the time, speed of light in air, always the same. And it's always this right here. It's 3 times 10 to the 8th meters per second. And so IB doesn't like to do the, you know, division. So they make it meters times seconds to the negative 1 power. And so I need to rearrange this equation because I'm trying to solve for this frequency right here. And so when I want to solve for frequency using this equation, frequency is going to be the speed of light divided by the wavelength. So you can rewrite the equation like this to solve for frequency. And then it's just a matter of plugging your numbers in, which is what they did. So they have speed of light here on top, which is that 3 times 10 to the 8th. And then the wavelength that's already been converted to meters is on the bottom. And when you divide that, you're going to get this number. And then the units for frequency, they're inverse seconds. So it's seconds raised to the -1 power. And then they gave it another unit name. So instead of seconds to the -1, sometimes you might see frequency represented as Hz, which Hz stands for hertz. So hertz and inverse seconds are the same measurement. It's just they took inverse seconds and they like gave it a new name, okay? So if you see hertz and seconds to the -1, you don't need to change the number or anything. It's the same value. So once you solve for the frequency, which is what they did, then they used this frequency in this equation to multiply by Planck's constant. So depending on the type of problem, if they, like I said, if they give you the frequency, then you only need to use this equation to calculate the energy. If they give you the wavelength, then you're going to have to use this equation first to calculate the frequency. And then you take the answer that you got for the frequency and you plug it into the second equation here. So again, when you read your problem, you know, make sure like this one, they gave us a wavelength. So that tells me, oh, this is going to be 2 steps because I'm going to have to use both equations to calculate the energy. And so this is what they said is they have in the, if you read the whole problem, in the hydrogen emission spectrum, the transition from n equals infinity to 1 produces a line in the UV spectrum with a wavelength of this, and that's the convergence limit. And so they're asking us to calculate the energy. And so that's the steps that we would have to go through. Now, this answer right here, this is the energy, okay? They also might ask us to do a mole. So if they wanted us to do for a mole of hydrogen, what we would do is we would multiply the energy we get by Avogadro's number, because they want to know how much energy per mole of a substance, okay? So just be aware that if they ask you for the energy per mole, then you need to multiply your energy calculation by Avogadro's number to convert it to how much would be per mole. So you have some practice questions there that you can answer. And then on this next page, you're going to use this link, and I put it on Canvas. It's in the page on Canvas where the notes, you're going to use this link and you're going to go to this website, and it has kind of a little database with some information about different elements. And so it's going to guide you through this, but because it's going to help you to calculate ionization energy from the convergence limit for some different elements. So it's going to have you do hydrogen first. And so it has kind of an image on here to help guide you that looks like the website. You'll click over here on energy, you'll click hydrogen first on the periodic table, then you'll click on energy levels, and it says scroll to the bottom, and then it gives you the convergence limit, and so that's the value you need. But this value, it's called the wave number, and so to calculate the wavelength from the wave number, it says take the reciprocal. So you're going to do 1 divided by that number to get the wavelength. And then on here on number 5, it says now that you have the wavelength, you're going to do just like we did on that example. You're going to you're going to use the wavelength to calculate the frequency using that first equation. And then, and it says using the equation below, but it's not really below. It's that one from up in the notes, the energy. So you'll use the energy equation to then find the energy to remove 1 electron. And then it says multiply by Avogadro's constant to get the energy to remove 1 mole of electrons. So on number 5, you're doing exactly like we just saw on that example. You're just using this value from the little website that it's going to have you go to. And then part 2, then it's going to have you choose 2 other elements. You can choose whatever 2 you want, and you're going to do the same, those same 3 steps. You'll calculate the frequency from the wavelength, then you'll calculate the energy from the frequency, and then you'll calculate how much for 1 mole of that element, okay? The only thing it says is it says to be sure when you go to the other elements, make sure you're clicking on the energy level that's underneath neutral atom. You don't want the one that's already been ionized, okay? And then it says compare your answer value to the data booklet in table 8. I'm going to post it. I forgot to post the data booklet on Canvas, but I'm going to post the file with the data booklet so that you can do that part as well, okay? All right, so what does this mean, okay? Well, when we look at ionization energies, we're talking about the amount of energy required to remove 1 electron, okay, which would turn something in from an atom into an ion. So we can see patterns, and we're going to get more into this when we get to topic 3 with the periodic table. But what we kind of need to see is, and this example here is talking about aluminum, okay? So we need to think about, okay, aluminum's atomic number is 13, and it's in group 3A or group 13, whichever whichever, you can call it group 13 or group 3A. So its atomic number, I'm going to put Z, atomic number is 13. It's in group 3A or group 13. The reason that's important is because we can see patterns in its ionization energy, and we can read these graphs and we can actually tell from these graphs what group an element is in based on the changes in its ionization energy. So on this graph, down here on the bottom, it says the number of ionization energy. So that means like how many electrons have they removed? So here, this is called the first ionization energy. So that's how much energy that it takes to remove that first electron. Then as you go to the second one's going to require more energy to remove because it's already stable. Okay, it requires more energy because there's more protons in the nucleus pulling on the electrons now. Then if I remove a third one, it goes up a little more. But then look what happens right here after the third one. There's a bigger jump. The line is a little more steep. It's got a higher slope. So what you're looking for in this graph is every time there's a steeper slope like this, that's your clue that that's what group the element is in, okay? Because if you think about it, aluminum has 3 valence electrons. If we write its electron configuration, it's 1s2, 2s2, 2p6, 3s2, 3p3, right? And so, or I'm sorry, 3p1, 3p1. So this is aluminum's electron configuration. And so if you look, the highest energy level is the third energy level, okay? And there are 3 electrons in there. So that means it has 3 valence electrons. So that means in order to become a stable particle, aluminum wants to lose 3 electrons and have a +3 charge. So these first 3, those are these first 3 here that I'm going to circle them in orange so it's a different color. These first 3, those are these 3 electrons. That's why there's a big jump here, because now after that third one, it's at that point, it's stable. So it really doesn't want to lose any more electrons. So if it loses a fourth one, it's going to require a lot more energy than the other 3. So that's why we see a steeper line, because it goes up a lot more, because now it's losing one of these electrons that's here in this 2p6. It's on the second level, and it really doesn't want to do that, okay? But then if you notice, once it jumps, then all these are pretty steady, because this is 1, 2, 3, 4, 5, 6, okay? And then these 2 are these 2s2. And then look, there's another big jump, because now we're changing energy levels again. Now, after that point, we've gotten rid of all the second energy level electrons. And so then the only 2 that are left, these 2 up here, those are the ones from the 1s2. And so what we can interpret from these graphs is every time there is a bigger jump, like here and here, that implies we're changing energy levels. Okay, so wherever the first big jump is, which is right here in this one, that is where I can figure out what group my element is in. So because this one had a big jump after the third electron, that tells me that it had lost 3 valence electrons, and it would be in group 3A or group 13, okay? And then the fact that it had 13 altogether, if I count all the dots on this graph, there's 13. That tells me that I can probably figure out that it's aluminum because it's lost 13 electrons, okay? And that's aluminum's atomic number. And so that's kind of what all is summarizing down here. It says electrons are removed from the energy level furthest from the nucleus first. So for aluminum, that's the third energy level. And they're further away, so they require less energy to remove. As you get closer to the nucleus, they're held tighter by that what we call the electrostatic attraction. And so further from the nucleus, there's not as much energy holding them, and so it requires less energy to remove them. And then as we remove them, it increases. And then once we remove all of them from the third energy level, then it says they remove from the second energy level, but it says notice the jump between the third and fourth. That's evidence of the existence of energy levels. So that's how we know there are different energy levels. Because if there weren't energy levels, like if they were all in the same area or the same level, there wouldn't be those jumps every now and then. And so that's how we can tell that there are energy levels, is because of those big jumps in energy between some of the removals of the atoms. And so then it says the electrons being removed are closest to nucleus. they require the most energy to remove because of the strong electrostatic attraction. So that's why at the very end here, there was another jump to remove the last 2 electrons that were on the first energy level, okay? And so if you look here, is this talks about the 4th to the 11th ionization energies, and this is really going into detail like I talked about where between 9 and 10, there's another, there's another gap here because these are going to be your 2p, okay? So like it says here, electrons removed from the 2p sublevel, and if you count, there's 1, 2, 3, 4, 5, 6, right? Because every p sublevel can hold 6. And then after that, excuse me, so it says the jump in energy between the 9th and 10th occurs because the 10th electron is removed from the 2s orbital, which is closer to the nucleus, okay? So it experiences a stronger electrostatic attraction. And then the bigger jump, there's a slightly bigger jump between 6 and 7. If I look again at this graph, it's not as noticeable as like between 9 and 10 or between 3 and 4, but it is the slope is a little bit steeper between 6 and 7. And that has to do with where the electrons are in that p sublevel, because if you remember back to our orbital diagrams, remember p, any kind of p sublevel, they have 3 orbitals. And so if it's full, if there's 6, it looks like this. So if I remove 1, 2, 3, those were all, the down ones. But if I remove another one now, it takes more energy because now I'm removing it from a singly occupied orbital. So that's why here between these two, there's a slightly bigger gap, is because the electrons being removed first were these 3. And so they're all about equal energy. But then once I get rid of those 3, the next one is going to require a little more energy. And so there's a little steeper jump. Okay. So at the end here, you have some practice where you're kind of interpreting some of these graphs. So it says, from the graphs of successive ionization energies, explain which group on the periodic table these elements belong to. So again, what you want to look for is where is the first large jump? So, where is the biggest difference, the steepest slope? And wherever that first big jump is, look between which 2. So it's going after, so like for example, this one, it's occurring after the 4th one. This one, it looks like after the 6th one. And so that's what you want to look for, okay?